Hello, friends. Welcome to Science Talk. I'm your host and resident oceanographer, Jim Assa. So, I've got two articles here, kind of talking about the same thing. So I thought it'd be a good idea to discuss them together about what's going on with the oceans. Namely, the oceans are becoming stable. People say, well, isn't that good? No, stable, no disruption, stuff like that. In the context that I'm going to discuss it with you, is a very bad thing. So this first article, it's in Newsweek, whatever. But the only reason I'm discussing this is because this is Michael Mann's work that they're discussing here. So they had an interview with Michael Mann. So we're warming the planet, right? And what happens is the surface and lower atmosphere is warming faster than the air aloft. That favors heavy, colder air on top of lighter, warmer air, a less stable atmosphere. It means more turbulence because you're going to want to have that cold air sinking, so you get that vertical overturn. Right? You're going to want that, though not want it, but that's what's going to happen, leading to instability, storms, that kind of stuff. And it's part of the reason that more extreme weather events are taking place. With the oceans, it's the opposite. The warm, lighter surface waters are warming faster than the cold, deeper water, since heat penetrates slowly down into the depths of the ocean. Global warming is consequently tending to make the oceans more stable. Now, we've heard me discuss before, and I just did a lengthy video on overturn mixing stratification. Go check it out if you haven't seen it. And it's a lengthy video, so if you want to watch it over a course of several days, fine. You don't have to sit through it in one go. But what we have going on is, as I discussed in that video, the density of seawater depends not just on temperature, but also salinity, how much salt is in it. Fresh water is lighter than salty water. The melting of ice is leading to the accumulation of the fresh light water at the surface, especially at higher latitudes. I have discussed this numerous times in these videos. Those of you who've been following me for some time, I think by now you're all experts as well. So it's a double whammy, with both the heating and reduced salinity leading to a more stable ocean. My colleagues and I, this is Michael Mann, just published an article in the journal Nature Climate Change showing that the oceans are not only becoming more stable, doing so faster than previously thought. Once again, we're now finding, and I've been stressing this point recently, that the changes are increasing exponentially, not linearly. And we have it right here. Led by Guanqiang Li of the Institute of Atmospheric Physics in China, our team, which includes Li Cheng, Zhang Zhu, International Arctic Research Center here in Fairbanks, Kevin Trenberth, and John P. Abraham, analyzed a quantitative measure of stability known as stratification. We found that the stratification of the world's ocean is not only increasing, doing so at a greater rate than estimated in previous studies. Our study uses more comprehensive data, more sophisticated model for estimating stratification changes. We found a nearly 6% increase in the stratification of the upper 200 meters of the world's ocean over the past half century. Let's pause there. As I discussed in that, what I call the OMS video, overturn mixing stratification, in order to have productivity in any aquatic body, you need two events. You need mixing, so you can mix the nutrients up from below into what will eventually turn out to be the photic zone. Photic zone is how far into the water column sunlight energy penetrates. Usually, the stratification will occur, usually, not always, but you typically, especially in temperate and tropical areas and in lakes, at the bottom of the photic zone is where the stratification will tend to take place. You get up into the polar region, you got haloclines and other stuff, that's not always the case. But you need the mixing, you need that overturn, followed by the stratification so that the phytoplankton, the nutrients, are then locked into the photic zone. Now, you may get some turbulence in the photic zone, in the upper water layers. They're still staying in the photic zone. They can still do photosynthesis. They can still carry on primary productivity. But now what happens if we have a continual stratification? Then you don't get mixing. You then don't get the nutrients into the upper layers. The phytoplanktons need the nutrients. Nutrients run out. Phytoplanktons die off. Primary productivity tanks, which means secondary productivity, tertiary productivity also tank, which means the food web, the food chain collapses. And throw in the fact that phytoplankton provide 55 to 80% of all the oxygen in the atmosphere, oxygen that we breathe. So if the phytoplankton start dying off, and the oceans are suffocating, as we say, the oceans are dying. Let's be blunt about it. The phytoplankton start dying off, that's less oxygen into the atmosphere, less oxygen for us to breathe. And by the way, atmospheric scientists have now measured a decline in oxygen content in the atmosphere. This is extremely alarming. When you look at regions of the ocean like the tropics, where you have a lot of sunlight energy there, you pretty much almost have a permanent thermocline in the upper layers. And that's why, because you have that thermocline there, and it's thermocline because temperature is not, the salinity tends to be stable, so it's more of a thermocline. We could say the general pycnocline term, that'd be fine. But it's more the temperature that determines density differences. And because you have almost that permanent in the upper 100 to 150 meters or so, it's very little productivity in the tropical waters because, well, you can't get mixing in of nutrients. You just can't. Temperate zones, yeah, you get more productivity in the temperate zones. But then don't forget, the middle of the ocean, the gyres, very, very little biological productivity there to begin with. But now we're starting to see that the temperate zones are warming up, so that what would have been typically a seasonal pycnocline, and we expect that to break down and you get the mixing later on, that seasonal pycnocline is turning into a more of a permanent pycnocline, thereby also reducing the productivity in temperate waters. Then you're losing the sea ice, so you don't have the ice edge productivity, so we have reduced productivity in Arctic waters. We're sensing a pattern here. Not good. So, continuing on. The more stable the upper ocean, the less vertical mixing that takes place. What I just explained. This mixing is the primary means by which the ocean buries warming surface waters, so the surface warms up even faster. It's a positive feedback loop. Okay. Now they're talking about with basically thermohaline circulation, right? Think of AMOC. You've got the water sinking. It takes the heat with it and carbon, right? It sequesters all of that. They don't mention what I just talked about here, mixing in the necessary nutrients into the upper layers so that the phytoplankton can carry on productivity. So this is bad for a number of reasons. As we currently watch the most active Atlantic hurricane season on record play out, that's something like over 20 storms, there are like 5 of them lined up. Key underlying factor is the anomalous surface warmth of the tropical Atlantic. The increasingly intense and damaging hurricanes we've seen in recent years have fed off warmer surface waters. More stably stratified waters tend to inhibit the wind-driven mixing up of cold, deeper waters that often serve as a sort of release valve, in other words, stifling the energy. Warm waters provide a lot of energy for storms. Interject some cooler waters in there, you may get some storms not as energetic, if at all. A more stably stratified ocean potentially favors more intense, destructive hurricanes. And we're seeing that. Harvey, Laura, right? We're seeing that. Warmer waters, and I have made this point numerous times, that gas solubility decreases with an increase of water temperature. So the waters will be less able to absorb CO2. which means at some point the CO2 is going to outgas back into the atmosphere, but also the solubility of oxygen is less. So the organisms, they need it for respiration. They're going to be stressed. Warmer waters absorb less atmospheric CO2. Less ocean mixing also means that less of the atmospheric carbon dioxide gets buried. That sequestration I just mentioned. So carbon pollution accumulates even faster in the atmosphere, causing yet more warming. Another positive feedback loop. Positive feedback loops are bad things in climate. And then if you start adding the outgassed CO2 from the oceans back into the atmosphere, you can call that a triple whammy. Finally, warmer upper ocean waters hold less dissolved oxygen. Less oxygen mixing means less oxygen and nutrients, since oxygen and nutrients depleted by sea life are less likely to be replaced from rising colder, more oxygen-rich waters. Everything I just explained to you. That has deleterious effects on marine productivity, right? You could shut off food chains, food webs, but fish population, right? The potential interruption of food webs and fish population that provide the main source of protein for more than 3 billion people. 38% of the world's population. They lose that source of protein, increase starvation. Dr. Mann and colleagues, our findings also have important implications of how much additional energy we may see in the future. State-of-the-art climate models used today to predict future climate changes tend to underestimate the stratification of the ocean. They consequently bury heat and carbon too easily beneath the ocean's surface. For that reason, they're likely underestimating the impact that the increased stratification, decreased mixing, found in our studies having on rising atmospheric CO2 levels and surface warming. So what he's basically saying is, folks, we need to adjust those models and include this new data and take this information into account. Our studies suggest that key positive feedbacks, amplifying factors related to reduced ocean heat, might lead to more rapid surface warming in the decades ahead than many of the models predicted. Decreased ocean carbon burial resulting from the reduced upper ocean mixing, moreover, could cause atmospheric carbon dioxide concentrations to build up faster in the atmosphere. Our findings lend credence to a recent study arguing we cannot rule out worst-case scenarios that some dismiss as exceedingly unlikely. Remember, I just did a video called Lessons from the Early Holocene, Eocene, where I talked that some new research says that, we've been whoppingly underestimating CO2 increases and thus how much temperatures will increase. It really is probably going to increase by up to 9 degrees C by the end of this century. Kind of what he's alluding to here. Where CO2 concentrations reach nearly triple pre-industrial levels, the planet warms up by perhaps as much as 8F by the end of this century. Well, 8F is a little on the conservative side here. Okay. 8F is about 4 to 5, about 4.5 C. In short, it's unwise to be complacent given the accumulating scientific evidence that climate change and its impacts may well be in the upper end of the range that climate scientists currently project, et cetera, et cetera. And, he's at Penn State and so on. So that's the summary of Dr. Mann's article. I want to bring up this article, which basically is talking about the same thing, but kind of reinforce the concept being presented here. Global warming is deepening blankets of warmer water that alter ocean currents, hinder absorption of carbon, intensify storms, disrupt biological cycles. So new study shows a vicious circle of climate change building on thickening layers of warm ocean water. What that means is the upper ocean water layers are becoming deeper. That's what thicker means. It's going deeper. Picture of a fisherman there. Near the surface of the ocean, Global warming is creating increasingly distinct layers of warm water that stifle seawater circulations critical for regulating climate and sustaining marine life. The sheet of warm water blocks flow of heat, carbon, oxygen, and nutrients within the water column and between the oceans and atmosphere. Right? And don't forget, we have the issue with the AMOC slowing and or shutting down. That adds to further stabilization of the water column. Because yes, you're going to get that fresh water there, and it's going to be cold because it's just melt water, and it's less saline, so you get that that stratification there. But eventually, the sun energy is going to heat that up. But you're still going to get the stratification there. And if you look at that OMS video I discussed at the end what happens. We looked at one of the graphics I looked at was AMOC running strongly with a weakened AMOC and how that affects the stratification, heat distribution, and other factors as well. A new study shows that more heat is building up in the upper 600 feet. We know that to be like a couple hundred meters of ocean, then deeper down. That increasingly distinct warm layer on the surface can intensify tropical storms, disrupt fisheries, interfere with the ocean absorption of carbon, deplete oxygen. Michael Mann. Okay, we just went through that article. The intensified layering called ocean stratification is happening faster than scientists expected. And again, it's referencing the September 28th journal publication, Natural Climate Change. So the deleterious effect will arrive faster and be greater than expected. The research suggests that some of the worst-case global warming scenarios outlined in major international climate reports can't be ruled out. Let's talk about. If the ocean surface warms faster and less carbon is carried to the depths, those processes, along with other climate feedbacks, could lead atmospheric CO2 to triple. Global average temperature could increase 8F by 2100. I'm going to say probably 7 to 9 C by 2100. The take-home point here is that, and by the way, Dr. Mann does tend to be on the conservative side. That's okay. But even now, he's realizing that maybe not be as conservative. The take-home point here is that once again, we are learning that the uncertainties are not breaking in our favor. Well, there's an understatement. If anything, the impacts of climate change are proving to be worse than we predicted. Increased stratification of the ocean could drive a vicious cycle of warming. If more and more heat stays near the surface of the ocean, the warm water will heat the atmosphere above. And if the layers of warm water slow the ocean's uptake of CO2, more heat-trapping CO2 stay in the atmosphere. Add to what I said earlier, you warm up the oceans, and then CO2 will be outgassing back into the atmosphere. So again, there's a lot of repeat information here. That's okay. There's a lot to take in, so it helps going over it twice. Okay. The overall stratification of the upper couple hundred meters, 600 feet of the ocean, increased by 6% in the last 50 years. Previous calculations measuring the change over time were not as accurate because they didn't include as much data, said co-author Li Cheng. So in the new study, the researchers used a whole bunch of new information, new data, from new instruments, taking advantage of new technology, and they got a better understanding of how the layers are changing all the way down to basically 2,000 meters. Now, recall a recent video I made where I showed you a graphic that showed how much heat energy the oceans have been absorbing over the last, over quite a few decades. And it just keeps going up and up and up. And we've got the information down to several thousand meters. And it's something I've been looking, to find that kind of information because when I was doing my research, we didn't have the technology. So, my work was, part of the work I was doing in addition to sea ice and was conducting heat budgets of the upper surface water layers. And oftentimes we look at polynyas as like a starting point. But now with the improved technology and computer modeling, we can really get a whole lot more information, really improve our understanding. Did you observe the increase in ocean stratification as yet another climate science prediction come true? Said climate scientist Stefan Ramstorff with the good old Potsdam Institute for Climate Impacts Research. He was not involved in this study. The increase in layering means there's less exchange between the surface and deeper oceans. I've discussed that with you before. You shut down the thermal haling circulation, you don't have that sequestering from the surface to deep depths. You're going to get, you're going to actually get some stagnation, and something that wasn't really brought up, but it can lead to hypoxic or anoxic conditions at depth. We did discuss the decreasing solubility of oxygen and how that puts stresses on the organism. Well, if you don't have the vertical mixing, you get the stratification. As you go down in the water column, you could find regions where hypoxic, low oxygen concentration, or anoxic, no oxygen concentration. And that, of course, would not be good for the organisms. And by the way, in my isotopic fractionation video, I discuss how looking at the isotope ratios, we can tell when there was thermal haling circulation happening and when there was not. We can tell, we can know what organisms were persisting or not because of that information. So if there was thermal haling circulation, we had an abundance of organisms and they were doing their thing. And we look at the, for example, the C13, C12 ratio. When the thermal haling slowed or shut down, we see a decrease in representation of organisms of fauna.
So we see changes in the C13, C12 ratios, as well as the O18, O16, and N15, N14 ratios.
Oh, it says here, if you don't have the, if you get the increase in layering, you don't have the vertical mixing, you don't have oxygen supplied to the waters below, you're not sequestering heat and carbon from the surface to deeper waters. Oxygen-depleted dead zones are already spreading in the oceans. I just said, right, about hypoxic, anoxic. Increasing stratification is slowing the steady, massive distribution of cold and warm water between the Arctic and the Southern or Antarctic Ocean. That's a reference to the conveyor belt. Conveyor belt is the heat distribution mechanism for the planet. But as that conveyor belt flows south, after AMOC, deep water formation in the Jin Sea, it eventually upwells in an area called the Antarctic Divergence. That brings nutrients, brings oxygen, brings a whole shitload of needed things. And that's why the Southern Ocean currently is the most productive open oceanic region on the planet. You start slowing down AMOC, you shut that thing down, you're not going to have that upwelling. You're not going to have all the nutrients and oxygen being brought to the surface water. Guess what happens to that very critical productivity region of the oceans? It collapses. And what do we find down there? A lot of the big baleen whales, right? Blues, fins, saybacks, humpbacks, right? As are all the other creatures. The pinnipeds, the orcas, and so on. Seals, right? The pinnipeds that eat the fish, etc., etc. Evidence is mounting the circulation system is already slowing down, as has been predicted by climate models. Right? And I've discussed that with you guys before. The vast system of ocean currents shunts warm and cold water between the Arctic, North Atlantic, and Antarctic Oceans. A disruption could lead to major climate shifts. If the current slows, more hot water could build up along the east coast of the U.S., leading to more coastal heat waves, rising sea levels, thermal expansion, right? Less warm water is transported northward. The climate in northwestern Europe, Scandinavia, UK, right, will become more volatile. It would cool down. According to a 2015 study published in the journal Climate Dynamics, impacts would include cooling in the North Atlantic, Northern Hemisphere in general, less precipitation in mid-latitudes of the Northern Hemisphere, large precipitation shifts in the tropics, strengthening of the North Atlantic storm track. The study also suggests that increased layering could affect ENSO cycles in the Pacific. Those multi-year warm-cold fluctuations affect temperatures around the world, with global hot spikes during strong El Niños and cool down during La Nina. I did a video on ENSO. But the growing stratification could suppress those cycles, leaving the Pacific in a permanent El Nino state. What does he mean that? Usually during the El Nino state, the upper surface waters are very warm, and that pycnocline is depressed. Warm upper surface waters, right, means you're going to have that warm temperature spreading all over the place, but also if you're depressing the pycnocline, instead of the pycnocline coming vertically up to the surface, bringing nutrients with it, what's called an upwelling. Same thing happens in the Antarctic divergence. That stuff upwells. The Peruvian anchovy fisheries, tanks. You have that issue. So that would not be good, having a permanent El Nino state. We know something like this has happened during the early Holocene, 9,000 or so years ago. His paper doesn't specifically address impacts of the El Nino cycle. There's only so much you could do in a research paper, right? The marine life, the impacts on marine life are more certain, said Kevin Trenberth, a climate scientist with National Center of Atmospheric Research. That's NCAR, located in Boulder, Colorado. Greater stability resists vertical movements and can have profound effects on fish, mammals. The nutrients from the bottom have to merge with the light from the sun in upper layers for high productivity. Increasingly stable layers may limit the rise of those nutrients. Exactly what I described earlier. That's kind of another reason why I wanted to look at this article, because it's discussed here. The other one, it was not. Equally important, how the layering affects the amount of CO2 going into the ocean. For now, oceans take about a quarter of the CO2 emissions from human activities. That is expected to decrease as time goes on. A warm upper ocean cannot hold as much dissolved gas. Doesn't matter what the gas is, right? Here's your double whammy, right? And then you increase the temperature of the water, whatever gas is already dissolved, we're going to outgas. The example they're using here is, a warm soda can't hold its fizziness. Cold one does, right? So oceans are less able to take up CO2 in the atmosphere, so atmospheric CO2 builds up faster. The ocean becomes less effective as a carbon sink. Oceans hold less oxygen, so that's bad for organisms. Temperatures increase in the upper ocean layer. Solubility of gases decrease, so then CO2 is going to outgas back into the atmosphere. So you've got the CO2 that's not being absorbed by the ocean, add to it the CO2 that had been absorbed by the ocean, but being dumped back into the atmosphere, and CO2 levels are going to spike. And we know when CO2 starts increasing rapidly, guess what happens? Guess what follows close by? Temperatures will start spiking. In that paper, discussed with you lessons from the early Eocene, discusses that very situation. Warm waters can't hold the CO2. You have all this outgassing. The temperature spikes with it. And then, of course, what we discussed a little while ago. Oceans hold less oxygen. It's bad for the productivity. It's bad for the sea life. You're going to start seeing collapsing of food chains in aquatic systems. And then, of course, as we discussed earlier, the effects on hurricanes is clear. The heat in the top 300 to 400 feet of the ocean is what fuels tropical storms. Strong storms really mix up the ocean, bring colder water to the surface that can limit the strengthening, perhaps even weakening the storm if it's cold water. Well, if it's all warm, it's going to increase the strength, not tamp it down. And even if that water is, cooler, it's not as cold as it used to be. It's warmer than it has been. That enables the storms to become stronger. That's why hurricanes are bigger, longer lasting, and more tense than before, and can rapidly go from a Cat 1 to a Cat 5, as we saw with Laura. So, excuse me. Wanted to bring this to you. Basically, things continue as we're going. Not just humans, but most life forms are kind of fucked. Be quite blunt about it. So there you have it. I try to in my discussions here, hopefully for those of you who saw my prior videos, you can now, start seeing the, how this all ties together, how the information, I don't want to use the word lessons, but for lack of a better term, the lessons I was trying to provide there all tie together so you can understand better what's happening in the planetary light system. BB, please go back and look over those videos of mine again. And for those who are interested, InsideClimateNews.org is the website. You go to home, and then you can search in there for ocean stratification and pull up this article and other related stuff. So thank you for your time. I hope you found this informative. Hello, folks. This is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.